Hello, my name is Conan Vargas, and in this presentation I will discuss the work entitled Evaluation of Structural, Ferroelectric, and Nanomechanical Properties of Aluminum-Doped Bismuth Ferrite-Based Perovskites Synthesized by the Solid-State Reaction Route. Introduction. At present, ferroelectric materials attract significant interest in functional materials research due to their ability to exhibit reversible electric polarization under the application of an electric field. Within this family, perovskite-type compounds with a structure of the form AbO3 have demonstrated remarkable properties. In particular, bismuth ferrite exhibits a distorted rhombohedral structure with space group R3C. This configuration enables it to display ferroelectricity and antiferromagnetism simultaneously at room temperature, a rare characteristic among multiferroic materials. Moreover, bismuth ferrite has the advantage of being lead-free, making it an environmentally friendly alternative to compounds such as lead zirconate titanate, which are commonly used in electronic applications but are associated with environmental risks. From a functional perspective, dielectric materials such as bismuth ferrite can be classified according to their physical responses into simple dielectrics, which store electrical charge; piezoelectrics, which generate an electrical signal when deformed; pyroelectrics, which respond to temperature changes; and ferroelectrics, which possess spontaneous and reversible polarization. Due to these properties, ferroelectric materials have applications in pressure or temperature sensors, ultrasonic actuators, non-volatile memory devices, energy harvesters, and microelectromechanical systems. However, pure bismuth ferrite presents some important challenges: the formation of undesired secondary phases such as mullite and selenite during synthesis, and issues like low density or high leakage currents, which limit its performance. To overcome these limitations, a common strategy is ionic doping, partially substituting A-site or B-site cations in the perovskite lattice. In our case, we chose to dope with 6% aluminum, a cation with a smaller ionic radius than iron, aiming to improve structural stability and functional properties without altering the overall valence of the system. Objective. The objective of this research was to reduce the synthesis temperature and enhance the ferroelectric and nanomechanical properties of lead-free bismuth ferrite-based ceramics doped with 6% aluminum, using the conventional solid-state reaction route assisted by high-energy milling. Methodology. The synthesis was carried out via the conventional solid-state reaction route. Two samples were prepared, one of pure bismuth ferrite and another doped with 6% aluminum at the B-site of the perovskite structure AbO3. Commercial high-purity precursors, bismuth oxide, iron oxide, and aluminum oxide, were used. The mixture was milled for 3 hours, uniaxially pressed at 300 megapascals, and then calcined at 725 degrees Celsius for 3 hours. Subsequently, a second milling, pressing, and sintering were performed under the same temperature conditions. The obtained samples were characterized structurally by X-ray diffraction with Rayet-Velt refinement, morphologically by scanning electron microscopy, ferroelectrically through polarization, electric field hysteresis loops, and mechanically via nanoindentation to determine hardness and elastic modulus. Results. Structural analysis. Doping with 6% aluminum stabilized the hexagonal R3C phase and reduced the presence of secondary phases such as mullite and selenite. Rayet-Velt analysis revealed a distorted perovskite-type structure, with a slight contraction of the unit cell when aluminum 3+ replaced iron 3+, due to its smaller ionic radius. Grain size. The average grain size decreased from 327 nanometers in pure bismuth ferrite to 246 nanometers in the aluminum-doped material, producing a more homogeneous and denser microstructure. Ferroelectric properties. The hysteresis loops showed a clear improvement in ferroelectric behavior. The remnant polarization increased from 0.201 microcoulombs per square centimeter to 0.695 microcoulombs per square centimeter with aluminum doping. This indicates greater mobility of ferroelectric domains and fewer non-ferroelectric phases. The coercive field also increased, suggesting improved polarization stability. Nanomechanical properties. Nano-indentation tests showed that the aluminum-doped material reached a hardness of 8.5 plus or minus 1.2 gigapascals, a Young's modulus of 128 plus or minus 3 gigapascals, and a creep resistance of 2.83 plus or minus 0.5 gigapascals. Under a load of 8.5 millinewtons, a residual indentation depth of 120 plus or minus 9 nanometers was observed, indicating homogeneous plastic deformation and lower porosity compared to the undoped sample. Pop-in penetration analysis. At low loads, the pop-in phenomenon, representing the transition from elastic to elastoplastic behavior, was identified. This analysis complements the mechanical data and confirms that aluminum doping improves deformation resistance without compromising material integrity. Conclusions. Reduced the synthesis temperature of bismuth ferrite via solid-state reaction by incorporating 6% aluminum at the B site. Stabilized the hexagonal R3C phase and decreased secondary phases molite and selenite. Doping with 6% aluminum reduced the average grain size from 0.327 to 0.246 micrometers, and increased the remnant polarization from 0.201 to 0.695 microcoulombs per square centimeter, with respect to pure bismuth ferrite. Achieved uniform deformation and lower porosity indicated by a residual depth of 120 plus or minus 9 nanometers under an 8.5 millinewton load. Enhanced nanomechanical performance with hardness of 8.5 plus or minus 1.2 gigapascals, elastic modulus of 128 plus or minus 3 gigapascals, and yield strength of 2.83 plus or minus 0.5 gigapascals. These results indicate that aluminum-doped bismuth ferrite has strong potential as a lead-free functional ceramic material, applicable in sensors, actuators, ferroelectric devices, and energy harvesting systems. Acknowledgements. The authors acknowledge the facilities provided by the Center for Research in Advanced Studies, Querétaro Unit, for the use of LIDTRA infrastructure through projects LN295261, LN254119, and LN299082, the collaboration of the Faculty of Engineering, Machis Campus, of the Autonomous University of Sinaloa, as well as the financial support from the National Council of Science and Technology, Project CB 2015 number 255626. Thanks for your attention. For more details, you may consult the full article in Inorganic Chemistry Communications using the DOI shown in the poster.